I'll discuss ExB vortex dynamics around a magnetic island, and this presentation is based on some recent work I did with collaborators listed here, all Asians, and also I acknowledge useful interactions with people listed here. So magnetic island turbulence interaction is a prime example of multi-scale interaction problem, which is also fusion relevant. So it includes many aspects of physics, and there are a few reviews on this topic. And this presentation focuses only on small part of various physics issues. And these are two main references. So I'll give you some long background of this study, and probably I will skip the second part, the theoretical methodology, because of time limits, and I'll explain the main results. So, Turing mode instability, the magnetic island can be spontaneously generated by Turing instabilities and equilibrium current profile. If we choose the rational surface and the mode number, we can calculate the quantity called delta prime, which characterizes the free energy associated with equilibrium current profile. And based on this classic paper on Turing mode, very elaborate asymptotic analysis by Rosenbluth show us that linear growth rate is proportional to fractional power of resistivity and almost linearly proportional to delta prime. So if we have a very large number of positive delta prime, we can have a strong classical Turing instability. And Turing instability is not just of academic interest, based on these studies. A few years ago, basically scaled down non-dimensionlessly similar to ether-based scenario mission. And based on these studies, Turing mode is a serious threat. And in particular, when there is no external torque to the plasma. So if you look at the statistics, if the average torque goes down, the number of plasmas, this is the plasma which disrupted due to classical Turing mode, because this is low beta n plasmas, this is not the neoclassical version. So many plasmas end up disrupting, so we have to consider Turing instabilities and magnetic island dynamics rather seriously. And magnetic island can be also driven externally by some coils or distortions in the boundary condition, and this is called the forced reconnection problem. And as you can imagine, this is a prototype problem of resonant magnetic perturbation physics, and there are a few experts on this subject. So RMP perturbation means you can mitigate H localized mode in H mode plasmas by inducing external magnetic field perturbation. So in that sense, magnetic island due to tearing instability is a major threat. On the other hand, we can, if we are creative, we can induce magnetic island so that we can stabilize some ExB instabilities, such as localized mode. And this is from LHD experiment in Japan. And basically heating time, history of heating and all those macroscopic external conditions are all the same, but one plasma ended up having magnetic island and another one did not have magnetic island. And surprisingly, the plasma with magnetic island ended up producing internal transport barrier, and it ends up with a higher central temperature. So even some spontaneously produced magnetic island can be beneficial to the plasma confinement. So I'll get into the issue of how magnetic island can modify the microturbulence in tokamaks. So as you can imagine, if magnetic island exists, it will flatten the profile, in particular across the O point radially, like this. And through X point, the profile modification is rather minor. So this is rather kind of expected one, confirmed in both experiment and simulations. And if you measure microturbulence from D3D tokamaks, you see that when you have a magnetic island turbulence, amplitude goes down nearly at O point region and goes up a little bit in X point region, but this is minor change. But what's important in the context of my presentation is that while the fluctuation near the O point goes down significantly, there is still non-zero finite fluctuation amplitude in the region where profiles are almost flat. And if you do nonlinear gyrokinetic simulations with static large size magnetic island and look at the structure of the ExB flow of various gyrokinetic simulations, report a vortex structure inside the island. And while this is a bit confusing, basically they are qualitatively similar for large size island. This is confusing because the GTC team in Beijing and GTC team in California couldn't agree on the sign conventions. So to do theory, we impose large static magnetic island, then nested tori of tokamak geometry flux surface get modified like this, and this is standard magnetic island geometry we learned from Paul Rutherford class paper, and we can define perturbed flux function due to magnetic island with helical dependence on angles. And also furthermore, we can define polar coordinate for this island. And from experiment, I think this is from TJ2, I hope Carlos is still here. And by looking at the Doppler shift of fluctuation, and you can map out the radial dependence of the Doppler shift by kind of changing the reflection layer. And you can deduce that the Doppler shift changes sign so that the vortex structure inside magnetic island going like this is compatible with this experimental measurement. So we believe there is E cross B vortex flow inside magnetic island. So first example of our calculation is how this E cross B vortex flow inside static large scale magnetic island is sustained. So we took this problem as a modification to Rosenbluth-Hinton problem of how axisymmetric zonal flow in axisymmetric tokamak geometry can be sustained in the presence of trapped particles and toroidal geometry and so on. So this problem is the helically symmetric vortex flow we initiated and ignore collisions, any dissipation, just put the equilibrium orbits into toroidal geometry and see how that relaxes. And so algebra becomes a bit complicated, but Kyungjin is very good at cranking out very complex calculation, and he found the answer, and the conclusion is that residual flow level is basically almost the same as Rosenbluth-Hinton value, but basically neoclassical polarization gets reduced due to the K vector modification in helically symmetric island. So actually conclusion is that it's well sustained. So this is now published in physical level vector.
When you say K, you mean K radial?
I mean, for helical structure, both. I don't know how to say.
I mean, one would think usually that you reduce the screening by squeezing the banana. Is what's going on? The island is somehow changing the banana width, or
No, banana width to the lowest order is the same banana we see in tokamaks.
Okay.
So what's different here is that usual zonal flow has only Kr.
Right.
But with the magnetic island, K vector has even, n is non-zero basically. That's
Okay.
one of the key. Toroidal mode number non-zero. It's helically symmetric, not axisymmetric. So the analytic calculation is about the same level as the Rosenbluth-Hinton calculation, and this G1 term is the modification comes from the fact that K vector of the magnetic vortex flow inside the magnetic island has non-zero n and m number. Okay. So we get higher residual level of vortex flow inside magnetic island compared to Rosenbluth-Hinton, but this is rather minor modification. And now second part is that many gyrokinetic simulations and even some fluid simulation which preceded this reported that microturbulence tend to spread into the magnetic island, and there are various nonlinear gyrokinetic simulations. So turbulence spreading physics probably initiated at least in fusion plasma context by Gabe and his French collaborators around here. But this example from GTC simulation is showing that the turbulence can grow in the linearly unstable region first and propagates into linearly stable region. Actually, this study was motivated by the fact that in the previous presentation, we discussed a little bit about the boundary condition at the pedestal, but what's not totally understood is the region called no man's land, somewhere between pedestal and the core. So we were emphasizing that in that connection region between edge and core, turbulence spreading can be important. And also, I think Carlos and others, Pat before that last week, discussed that ExB flow shear can reduce the turbulence spreading. And as ExB shear layer gets deeper, turbulence spreading extent can be reduced. But of course, more studies and scans and understandings are needed for this. So anyway, ExB flow shear can reduce the turbulence spreading significantly. And also experimentally, there are evidence of turbulence spreading. So there are evidence from these 3D documents, BES measurements at the L2H transition, and also examples from PJ2. I made this diagram before I listened to Carlos talk. So this was already explained between electron root and ion root, ER structure and turbulence spreading changes. And this is one of the main motivation for our work. Actually, Kasumi Ida visited this 3D and did the experiment, and he looked at both electron heat pulse and density fluctuation, and his conclusion based on the analysis of experiment is that at the X point of magnetic island, heat pulse propagate earlier than turbulence. On the other hand, at the O point of magnetic island, turbulence propagate earlier than the heat pulse. So conclusion is turbulence spread into magnetic island through X point. So I mentioned gyrokinetic simulations result, but there are also experimental evidence for this, and this is a bit more complicated, but this is from K-star, so I present this, and basically the conclusion is same, although color view graph is more complicated. Also, this is ECEI measurement of the electron temperature fluctuation. So to address the microturbulence spreading through the magnetic island X point, we use two-point decorrelation theory invented by Ellis for fusion plasma physics by late Professor Tom Dupree, unfortunately passed away 2 years ago. And I don't really have time to go through this. And this was first developed for 1D Vlasov system. And the Pat Diamond is the one who made this methodology quite popular in magnetic fusion community, including the big diamond theory and many other examples such as trapped electron mode and so on. So if I make an oversimplified cartoon of what this two-point theory can give us, so basically it describes how two nearby points in one small eddy can deviate from each other, and they are very close to each other. They feel almost the same force and must stay together, but after some time, it should deviate. Then by looking at the propagator of the governing equations, and by inverting it, you can see the footprint of the how eddy's shape was looking like by looking at the various moments, temporal evolutions, how they deviate, and their parametric dependencies, in particular their separation in various directions. So this is the doing this calculation in ExB symmetric tokamak, and we put some eddy of turbulence characterized by their size in radial and by normal, that means almost colloidal direction, and the effect of ambient drift wave turbulence is characterized by relative diffusion going like this. And we can basically utilize the method for many interesting problems. And many years ago, I did calculation for ExB shear effects in toroidal geometry extending PDT. So where is it? So basically, you end up solving this kind of equation, including the effect of ambient turbulence, drift wave turbulence, giving us the relative diffusion, and ExB shear flow, giving us the ExB shearing rate, going like that. And we basically can do the same calculation in magnetic island geometry as well. So it's going down. Okay, so introducing this magnetic island geometry again, for this quasi-helically symmetric magnetic island, geometry, we can also do the two-point correlation calculations. So this is the answer for the ExB shearing rate, and this is the result for shaped tokamaks, something now known as Hahm formula like this. And basically, we can do the similar calculation in magnetic island. We end up deriving this rather complicated expression for magnetic island. But for both cases, this kind of generic form of the ExB shearing rate is valid. Difference is that the flux function here is for the usual flux function in ExB symmetric and nested tori topology, but here a flux function is different one, and we put magnetic island geometry. So ExB shearing rate can be factored into these three pieces. One is magnetic island geometry specific geometric factor. Second one, underlined in blue, is the turbulence eddy shape in polar coordinate with magnetic island. So basically, you call it aspect ratio of the eddy. And the third part is the most obvious one. So this is slab version of just ExB shear. Okay, so without going through geometric details or eddy shape, one usually think about E cross B shearing rate as this. Okay. So first factor is concerned, this is basically magnetic island radial width over the local minor radius and times colloidal mode number. So even a very thick magnetic island in tokamak is still elongated in y direction compared to x direction. So that means E cross B shearing rate is rather strong in the middle plane compared to near the x point, because flow is incompressible, so it should slow down when it goes around the x point. Okay. And also the second factor even enhance this asymmetric inhomogeneous feature of the E cross B shearing rate. At the x point, this form factor actually vanishes. So at the x point of magnetic island, there should be no E cross B shearing rate, even if there is a E cross B shear present, just due to the geometric effect. So that is the main conclusion. And as I told you, this is the usual E cross B shear parameter in Cartesian coordinate. So you have to note that most experiments, they talk about E cross B shearing rate in their paper, but they're not using the full, of course, they did their experiment before our paper. And we are talking about only this term, okay, last factor. So when we want to interpret the experimental data, makes more sense to think about geometric corrections further. So if I make the long story rather short, this is the cartoon summary of our calculations. So our E cross B shearing rate calculations indicate that turbulence must spread into magnetic island through X point. On the left, I try to describe the local gradient-driven turbulence by red color. And basically, if you flatten the profile here, just outside of magnetic island, you end up steepening the gradient. So turbulence gets a bit stronger just outside. And blue is the strength of the E cross B shearing rate we just calculated. So if you look at the E cross B shearing rate inside magnetic island for E cross B vortex flow going around, just due to the geometric effect, E cross B shearing rate is strong in this region, but gets very weak at the X point region. So as a conclusion, the turbulence will penetrate through the X point and go into the interior. So this is my scientific cartoon. Okay. So see, we would like to claim that this our calculation provides a plausible explanation of this experiment on D3D. And also there was lots of discussion about the turbulence spreading now into the scaffold layer and how that might affect the devoter heat load and things like that. And there is a recent work from LHD that actually some low M magnetic activity can kind of partially destroy pedestal and increase ambient turbulence in that region and make a stochastic layer. And this might be a relatively a possible new scheme to reduce peak value of devoter heat load. So this is another example how turbulence spreading is influenced by E cross B shear and what kind of interaction between magnetic island and microturbulence can occur in the presence of E cross B shear and so on. And so I only assumed very simple monopolar E cross B vortex flow inside magnetic island. And sometimes that's to the lowest order justified for static and very large magnetic island. But there are many other studies looking at the E cross B vortex flow. And sometimes for thin island, vortex flow structure gets more complicated. And Youngjin Choi has no shortage of energy in cranking complex algebra. And we noticed that as I told Pat, the E cross B vortex flow inside magnetic island has non-zero toroidal mode number and non-zero colloidal mode number, since magnetic island itself is quasi-helically symmetric. So if you look back Rosenbluth-Hinton calculation of the axisymmetric zonal flow, because that's axisymmetric, the toroidal precession of trapped particles don't interact with zonal flow because zonal flow has n equals 0. But here, for vortex magnetic island, inside magnetic island, toroidal mode number is non-zero. So if you look at really long-term slow time scale of inverse of the toroidal precession of trapped particle, the precession can basically modify the vortex flow evolution, and the simple and nice vortex flow structure gets modified, and we get somewhat messy profile of vortexes becoming partially dipolar. I don't know how to describe this. And so this was a bit, I like some simple answers. So at first I wasn't very, can I say, just emotionally I wasn't happy, although professionally, scientifically I was happy to see new results, but just personally I felt, oh, this is a bit ugly. But I found out that this could provide some answer between some different conclusion between Gene and GTC. Of course, they usually don't agree, but I can facilitate their results because Gene simulation reports that there is some threshold of magnetic island radii width, and if island is bigger than the threshold, monopolar vortex exists, but island thinner than threshold, there's no monopolar vortex. But GTC reported nice looking monopolar vortex for below threshold. But if we combine our result due to this toroidal process precession and their validity regime due to the fact that we ignored the parallel transport inside the magnetic island, we can deduce the magnetic shear and Q dependence of the that threshold. So they can reconcile these two gyrokinetic yields because they use different value of Q and magnetic shear. So basically these are the two gene and GTC simulation I am talking about. So maybe I should do. So basically, how am I doing in this time?
In between 5 and 10 minutes.
So basically, I already have told you my main story, and of course the question is what happened to the nonlinear Turing mode evolution, and from Paul Rutherford we learned that the flow pattern around the slowly growing magnetic island should look like this, and of course many fluid simulations and also some analytic calculation confirm this when magnetic island grow. And I now record Dominic suggested something last year. I printed out that paper, but somehow never had time to get into it. So that's another outstanding issue of how magnetic island evolution gets modified by microturbulence and associated ExB flows. So let me conclude. We calculated the ExB shearing rate is inside magnetic island, and it may offer some plausible explanation how the turbulence can penetrate into the magnetic island through the X point. You remember that this 3D experiment measurement has shown that even inside magnetic island, near O point, microturbulence level was non-zero. And so our result can be useful for more quantitative interpretation of the results from experiment and simulations in future, including the studies of transport bifurcation. So magnetic island geometry can actually facilitate the transition to enhanced confinement regime. There are some experimental data supporting it, but not always magnetic island is beneficial for the transport barrier formation. So Ida-san's speculation is that since the magnetic island makes the heat flux going out becomes more concentrated near the X point, actually that makes the exceeding the power threshold much easier. So this is rather interesting, but arguable argument. And also, when was that? It was 2019 fest. I remember Pat was working with his Chinese young colleagues on how the dynamics around magnetic island, ExB shear and so on, can actually lower the critical value of the threshold for transition to enhanced confinement regime. So I think this is very interesting problem, and if you have enough interest and energy, please look at this problem. Okay. Merci beaucoup. C'est tout.
Does the magnetic field line stochasticity play any role? I would expect that to be concentrated areas.
I mean, my own work did not consider any stochastic setting. But to be realistic, maybe near the X point of magnetic island, maybe flux surfaces are not really well defined, to be fair.
Once the turbulence penetrates inside, once the turbulence penetrates in the island through the X points, presumably there is some homogenization on the magnetic surfaces on the limit. So the question is, what is the final state of the turbulence intensity within the island? Is it symmetrical or not at all?
I mean, one can speculate about this beyond the scope. And also one has to address how the turbulence can generate the ExB vortex flow and so on. So there are many feedback loops, and I'm just looking at just a couple of them here. So it's not really complete and truthful. So worthwhile to think about.
So I will first on a follow-up to Xavier, I would think from what we understand about homogenization, you'd have a 2-time scale process where you would very rapidly form, equalize on island flux surfaces, and then a much slower cross field thing. So I think there isn't a single time scale, right? And it would take probably a while to homogenize across the entire island. My guess it would be back to the 1/3 thing with magnetic shear and with whatever residual diffusivity in the island. But I mean, the critical question in this, which is still hanging, is this last point of there are 2 states, right, that Ida points toward. Well, he reverses the high and low, so it gets confusing.
Yes.
But there's a high accessibility state where the stuff spreads in, and there's a low accessibility state where it doesn't. Right? And what is the valve? Right?
I mean, how many times you ask me that? I mean, why don't you solve it? I mean, you and you also have more younger
we just
generation collaborators in China.
The first paper from last time, finally, a few weeks ago. So maybe we'll get to the second one. But that's the critical question in this, right?
No, of course, that's a critical question.
And let me, have you considered if you have an array of islands that are not overlapping, what would happen?
No, not yet, but can think about it. Yes.
One would think that the heat would flow basically along the contours of a web around the islands, right? But would not be able to penetrate if you're above the critical, the critical level, would not be able to penetrate into the island.
So things like magnetic island version of Los Angeles that were same type of
Yeah, you'll see. We looked That's Freddie Ramirez next week, if everything, time zones and connections work. We looked at the interaction of, well, the heat penetration into a vortex crystal and allowing the vortex crystal to vibrate. So it has some controlled level of stochasticity. And that's exactly, you get exactly the focusing, right, between the vortices, and you get a web. And then if you want to make a color picture, you can even get a staircase out of that quite easily. So I mean, it suggests this point of focusing of the and this is all, by the way, with a passive scalar, nothing complicated, but it suggests this point that Ida made in 2003 of the focusing of the heat around the X point is really critical. And probably the degree of that focus is what controls the threshold. So.
So in the case where the island is produced by an external magnetic perturbation, then this flow story sounds really okay. Now, in the case where the island results from an instability, there might be a competition with the quadrupolar velocity flow, which is necessary to sustain the island, because the X point exists because there is a converging flow bringing magnetic energy there where it is dissipated, and the O point exists because, to the contrary, there is a return flow which is opening up the separatrix. So in the linear stage, you show the picture with big vortices which occupy island width. In the saturated state, numerical simulations show that the vortex is strongly concentrated next to the X point and along the separatrix. So in the center of the island, there is almost no flow. It's concentrated next to the X point. So there might be a competition between your nice vortex and this quadrupolar structure in the case of a self-organized island.
Yeah, that's fair and good point. And also that there are vortex produced by microturbulence. So I think Ishizawa and his collaborator did various fluid simulations, and actually I recall he has shown both cases, one dominated by vortex structure, which is monopolar, and the other one, like what you are talking about, a sustaining Rutherford Island kind of thing.
The island in a self-consistent simulation or situation, is the island always rotating at the same speed at the radially as the turbulence eddies, or could it be different? And in this case, would that play a role in the spreading or just the entrainment of turbulence inside the island? Just in the polynomial direction in this case,
I
not
think
radial.
most nonlinear gyrokinetic simulations were performed with some initial static magnetic island. So this is not totally self-consistent. But on the other hand, there are fluid simulations which put both island and ITC turbulence together and let them evolve, but but their dynamics is kind of approximate. So that should be looked at in the future.
Okay, no other question or comment. Let's say yes again.